In this lesson, we are going to review for your second midterm, which covers the contents of chapters 6, 7 through 9, and mostly deals with probabilities and probability distributions. So first we're going to do some probability questions, and I would suggest trying them on your own and then seeing if you got them right. So Jan is a member of a class with 35 students that meets 5 days per week. A student in Jan's class is randomly selected to explain how to solve a homework problem every day of the week, and once a student's been selected, he or she is not picked again that week. So if Jan was not one of the 4 people selected earlier in the week, what's the chance that she'll be picked on Friday? So this is just a really, really simple one. So you need to figure out how many people there are to pick from on Friday. So how many left on Friday? Well, there were 35 total, and 4 days went by, so there are 31 people left, and Jan is one of them. So the probability that Jan gets chosen on Friday is 1 out of those 31 people. And it's okay to leave your probabilities as fractions. You don't have to change them into decimals. Casino games often use a fair die that has 6 sides with 1 through 6 dots on them. And the die is tossed or rolled. Each of these 6 sides is equally likely to land face up. We're going to pretend that that die is not loaded. Using the physical assumption that the die is fair, find the probability of each of the following outcomes for the number of dots showing after a single roll. So what are the chances you're going to get a 1 or a 5? Well, the probability of a 1 or a 5, that's 2 different possibilities out of 6 total, which reduces to a third. Well, an even number of dots, that means you get a 2, a 4, or a 6. And that's 3 out of the 6 options, or probability 1/2. So over the long run, you'll see an even number half of the time. Suppose a student is asked to choose a number from 1 to 10. Define A to be that the student chooses the number 7, and B to be that the student chooses an even number. So remember that the even numbers are 2, 4, 6, 8, and 10. So what is probability of A and B? In other words, what's the probability you pick a 7 and you pick an even? So these aren't 2 separate students. This is like if you are the student being chosen, what's the chance that A and B are both going to happen at the same time? Well, this is 0. You cannot be even and 7 at the same time. Are the events A and B independent? Now the best way to check this is to check, does P of A and B equal P of A times P of B? If so, then independent. If not, not independent. So we just found P of A and B in part A, that's 0. Now P of A is the probability that you choose a 7. Well, that happens with probability 1/10, one number out of 10. We're assuming that you're choosing numbers completely at random and there's no sort of weird bias going on. Probability you pick an even number, well, that's 5 out of 10 or a half. So 0 is obviously not equal to 1/20th. So thus, A and B are dependent. So are these events A and B mutually exclusive? Explain how you know. Well, 2 events are mutually exclusive if they do not contain any of the same simple events. And here a simple event is just a single number. So 7's a simple event, 2's a simple event, 4 is a simple event. And you can see that A is just the event consisting of 7, and B is the event consisting of 2, 4, 6, 8, and 10. And these 2 events have nothing in common, which means they're mutually exclusive. So yes, A and B do not share any simple events. You could also say that there's no overlap between these two events. That's kind of the same thing. So Julie, poor Julie, is taking both calculus and statistics. And we're going to suppose that at the outset of the term, the probabilities for her getting A's are as follows. The probability of an A in calculus is 0.3, and probability of A in statistics is 0.7, probability of A in both is 0.2. You could have found this from, say, I don't know, your teacher's data or something like that. So question A, are these things independent? Explain how you know. Well, we're told P of A in calc and A in stat is equal to 0.2. And let's check and see what is P of A in calc times P of A in stat equal to. Well, calculus 0.3, statistics 0.7, it works out to be 0.21, and oh, so close, but not quite. Close doesn't count. They have to be equal to be independent. So, as these numbers are unequal, the events are dependent. Sad. So part B, find the probability that Julie will get at least one A between her calculus and statistics classes. So what this means is she'll get either an A in calculus, an A in stats, or both. And that is an or statement. Probability of A in calc or an A in stats. And this, remember, or translates into addition, probability of A in calc plus probability of A in stats. And you have to take away the probability of A in both. This is the rule P of A or B equals P of A plus P of B minus P of A and B. And the way to think about it is this little diagrammy thing. Over here's event A, over here's event B. When you count the probability of an A in calculus, that's all this stuff. And when you do the A in stats, that's all this stuff. And you see you got this middle overlappy bit, you got that twice. And that's why you have to take it away. Okay, back to our specific numbers. A probability of A in calc was 0.3. A in stats was 0.7. Minus both, which is 0.2. So that comes out to be 0.8. So that's an 80% chance that this person will get an A in either calculus or stats or both. Okay, this one's a bit tricky. I did it wrong myself until I thought about it more, so let me see if I can explain it. Two students use a random number generator to pick an integer between 1 and 20. What's the probability that they pick the same number? And here is what it's not. It actually isn't 1/20th times 1/20th. I know this is weird, but this reason is that, say you can pick 1 and 1, you can pick 2 and 2, you can pick 3 and 3, etc., 4 and 4, 5 and 5, and 20 and 20. And this is just one of those. It's like the chances first person picks a 1 and second person picks a 1. You have to do it again for person who picks a 2. And you'd be adding this expression to itself 20 times, or multiplying this by 20, which comes out to be 1/20th. And another way to think about that is you have your first number spot and you have your second number spot. This number can be anything. So you just say, okay, well, probability of 1, anything. Because that's saying any of those numbers is possible. Each has probability 1/20th, so 1. And then the second one, this one must match. And once you've picked that first one, to make that next one match would be 1 out of 20. Now that's tricky. And if you had said 1/400th and it was like a 2-point question on a test, you definitely give half credit because it's just tricky. What's the chances that they pick different numbers? Well, that's the complement. Probability of same plus probability of different would equal 1. So probability of different would equal 1 minus probability of the same, or 1 minus 1/20th, or 19/20ths. That complement rule is the trickiest one to see, and this example is going to use it as well. So suppose the probability of winning a particular casino game is 0.15 and it's independent from one game to the next. If someone plays the game 10 times, what's the chances they're going to win at least once? And remember that at least once means they could win once, they could win twice, 3, 4, 5, 6, 7, 8, 9, or 10 times if they're super lucky. So if you found and did 0.15 to the 10th, this is a really common wrong answer. This is the probability of winning all 10, which is going to be super, super low, and that's not what you want. You have to think about what is the opposite, what's the complement of winning at least once? Well, what's the chances you win none of the 10? Well, the chances of not winning any individual game is 0.85. And because they're independent, we could say, okay, don't win game 1, don't win game 2, don't win game 3, etc. And each of those are probably 0.85. This is going to end up being 0.85 to the 10th, which comes out to be 0.197. So about 20% chance that if you play that game 10 times, you lose every single time. But the chances of win at least one sound much better. That's going to be 1 minus probability of winning none. Those two events are complements. And 1 minus 0.197 is 0.803. So you have an 80% chance of winning at least one of those 10 games or more. These problems are really cool because they're really real-life applicability. So we are going to probably have one on your test, just a fair warning. Suppose that only 2% of individuals undergoing a particular medical test have some disease the test is trying to find. And if an individual has the disease, the chances it's going to find it correctly is 0.99. And if they don't have it, the chances that they're going to have a false positive is 0.05. So first we're going to make the 100,000 table, and then we're going to make the tree diagram. So I have disease, and then I have, on this side, I'm going to have test result. You don't have to necessarily do it this way, just your tables must have the correct numbers in the sort of correct cells. I think what I mean by that. So there's yes, you have the disease, no, you do not. And there's a positive test and a negative test. That's your results. the 100,000 goes here. Now, the thing to start with is you know that only 2% of individuals have this disease. So this is my yes disease column. 2% have the disease. So 2% have disease. So take 100,000 times 0.2. So out of that sample of 100,000, you're going to have 2,000 who identify who have this disease. And the remaining don't. So take 100,000 minus 2,000, and that gives you 98,000 people who get this test who don't have the disease. Okay, so this was the first thing I did. This was the second thing I did. Okay, now next you know if you have the disease, the chances you're going to find it are 0.99. So that's the yes disease positive result. So this one. And of your 2,000 people who are sick, 99% of them are going to be identified as so. So you have 1,980 people here. And then, so that's my third thing. And then sadly, 20 people who have the disease are still going to test negative. Okay. Now we also know that if an individual does not have the disease, the chances of the test falsely gives a positive is 0.05. So that is positive test, no disease, so this one. So 0.05 times 98,000 works out to be 4,900. And then we have 93,100 people who don't have the disease and get the correct test result. Okay, and then just totaling across the columns, I have 6,800 and I have 93,120. And you can see that along this diagonal, those are sort of the correct results. Has the disease, gets a positive test. Doesn't have the disease, gets a negative test. This one and this one are problematic. And you can also see that of everybody getting positive tests, there are lots more people who are not sick than are actually sick. All right, let's do the tree diagram now. So you start, and this one makes sense to students more, so on the test I'll probably make you do both, but it's good to know more than one way to look at a problem. So the first branch in your tree is you have the disease or you do not. And the chances you have the disease are 2% or 0.02, do not 0.98. And then from that, the test results could either be you have the disease and you test positive, that happens probability 0.99, have it and you test negative, probability 0.01. Do not have the disease, test positive, that happens probability 0.05. Do not and get a negative test, that happens probability 0.95. And then multiply along each branch, 0.02 times 0.99, 0.0198. That's disease and a positive test. This will be 0.0002. I'm going to use some abbreviations here. D for disease, minus for negative test. 0.98 times 0.05 gives us 0.049. This is no disease positive test. And the last one, 0.931. This is no disease negative test. And these numbers should look pretty similar to the things in your tables. They're decimals and they're not whole numbers. If you were to take these numbers and multiply by 100,000, you get those numbers in your table. 0.931 times 100,000 is 93,100. So they are related to each other. And when you make these diagrams, please label what's going on. I mean, I don't care if you put do not on top and disease in the bottom, but make it pretty obvious what goes to what. Now this part B is easier to figure out from the table than from the tree diagram, so we'll go over both of them. So this is the question that the table and tree diagram is going to answer for us. If the test result for somebody is positive, what's the chances that this person actually has the disease? So what's the probability of disease given a positive test? And first, let's use the table. So you look at how many positive tests there are. Well, there were 6,800. And of those, how many were actually sick? 1,980. So probability of 0.288. So that's from the table. You just say, okay, well, out of my positive tests, this many people were diseased. You can also use the rule you have for conditional probabilities that says this conditional probability is probability of disease and a positive test divided by probability of a positive test. Now on your tree, the disease and positive test, that has probability 0.0198. And the tricky thing here is that there are two ways to get positive tests. You could have disease and positive test, or you could have no disease and positive test. So the probability of having disease and positive test is 0.0198, plus the other way you can have a positive test is to have no disease, and that's probability 0.049. And if you do this correctly and put parentheses where I wrote them in your calculator, you're going to end up with the same thing, 0.288. Either one. All right, the next chapter dealt with random variables, both continuous and discrete ones. So a discrete variable is like a variable that lands into like little boxes of categories. So for example, to make it really school-like, number of classes skipped this semester. We're not going to count half skipping differently than completely skipping, just skipping. Or number of cups of coffee a college student drinks in a day. So the point is that intermediary values are not possible. You drink a whole cup of coffee, you skip a whole class. So even though one could argue a little bit that you could drink partial cups of coffee, but we'll pretend like it's, discrete. Continuous, well, those are things like height, weight, stuff like that. So suppose the probability distribution for X equals number of jobs held during the past year for students at some school is given as follows. This is an example of a discrete random variable, because each job counts as a job. There are no half jobs. Working part-time still counts as a job. So find the probability that X, which is number of jobs, is bigger than or equal to 3. Well, this is the chances that you have 3 or more jobs. So the probability a student has 3 or more jobs is, okay, well, probability you have 3 jobs is 0.15. Probability of 4 jobs is 0.06, so 0.21. So the chances of an average student having 3 or more jobs happens is probability 0.21. Find the probability that a randomly selected student had 1 or 2 jobs. So we want the probability that x equals 1 or x equals 2. Note these events are disjoint, so it's either x equals 1 plus probability x equals 2. So 0.43 plus 0.21, 0.63. With discrete random variables, the or equal to's are important. With continuous random variables, they're not. So the probability that x is less than 3, this is the probability that a student has had fewer than 3 jobs, but not including 3. So that could be no jobs, probability 0.15, 1 job, probability 0.43, and 2 jobs, probability 0.21. So that's 0.79. And so the probability a student has fewer than 3 jobs is 0.79. And you could rephrase that. You could say probability a student has 2 jobs or less. That'd be fine as well. But when I say fewer than 3, that means 3 is not included. So next, let's find a table that gives me the cumulative probability distribution for x. So this is a function that accumulates probabilities as you go. So number of jobs is less than or equal to some value for k. And here we have the probability that the x is less than or equal to that k. So in this first entry, what's the chances you have 0 jobs or less? Well, that's 0.15. This next one is the probability of x being less than or equal to 1. So 1 job or less, which is found by taking this probability plus this one, and gives us 0.58. This next one, probability that x is less than or equal to 2. Well, that's this one, and this one. So you take your answer for your 1 and add on 0.21, which gives you 0.79. And then 3, well, probability that x is less than or equal to 3, now you add on this one, so you accumulate it, 0.94, and finally, this last one will be 1. And there are some pretty obvious patterns here, like this first number, it's always the same, right? This last number, once you get to that, you've exhausted all your possible events. So that happening, or probably that x is less than or equal to this number, is 1. It's a certain event. All right, suppose you play a game where the following table gives the probability distribution for x, which is the number of wins in 3 independent plays, and the chance of winning each game is 0.3. So first of all, what is the expected value of x? This is the same thing as the mean. So I'm going to say mu equals e of x. And the way you find this is you take the sum of your x's multiplied by their corresponding probabilities. So the first event is 0. Its probability is 0.4343 plus 1 times 0.441, 2 times 0.189, plus 3 times 0.027. So this works out to be 0.9. one thing to note, this was also a binomial random variable, just because of how I worded it. So independent plays, probability of success is 0.3, and for binomial random variables, the mean mu is NP, where N is the number of trials. So that's 3 trials times your success probability of 0.3 also gives you 0.9. It's the same thing. So the formula that I used first is more generalizable. It will work in situations where this is not a binomial random variable, but had you noticed this and done it the second way, you're not incorrect. Next, find the standard deviation. Okay, so the symbol for that is this good old Greek sigma squared. And this is the sum of the xi minus mu squared times the corresponding probability of that xi. So our first xi is 0 minus answer from part A, which was 0.9 squared times probability 0.343. Next x is 1 minus 0.9 squared, probability 0.441. Next, 2 minus 0.9 squared, 0.189, plus 3 minus 0.9 squared times 0.027. This works out to be 0.63. Okay, and technically sigma squared is this thing called the variance. And how that relates to standard deviation is that standard deviation is equal to the square root of variance. And the standard deviation symbol is just plain old sigma. So sigma is root of 0.63, which is about equal to 0.794. Now, once again, because this was binomial, with n equal to 3 and p equal to 0.3, we have a special formula for the standard deviation that we could have used here, and this is definitely faster. And that formula is sigma squared equals np 1 minus p. So 3 times 0.3 times 0.7, or 0.63. And once I gave this on an exam, and I had a bunch of students this way, and I thought that they were wrong, but I couldn't figure it, but they weren't, and so I had to go and regrade all those questions after I'd finished about half of them. But once again, the method that I did here, this will always work. This is special for binomials. Now, last thing, write a short sentence telling me what that expected value actually means. So you had that mu was equal to e of x, which was 0.9. Well, this is the number of games you would expect to win on average if you play lots of groups of 3. So over the long run, one will win 0.9 out of every 3 games played. And what that over the long run means is that if you play this game many, 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 many times, you will win. This is approximately 1 in every 3. Now those binomial random variables are a bit tricky, so let's deal with one of them. Suppose we have a treatment for a disease, and when this treatment's applied to a random patient, the chances that they recover is 0.7. The treatment is going to be applied to 5 patients, and we're going to let x equal the number of patients who recover. Find the probabilities for the following events. So we are assuming that this variable is binomial. how do we know this, and what are we assuming we didn't mention? So first of all, we know that x is binomial because we have two outcomes. Either you recover or not. And we have that chances of success, 0.7. We have 5 trials. And then what we're assuming, that we didn't say, we're assuming trials are independent. And what this means, in this case, the trials are patients. And so what you probably would have to assume is that there are no siblings, relatives, or twins. Dang those twins. Yeah, but what you're assuming is that independence that's required for binomial random variables. So what's the chances that exactly 3 of the individuals recover? So your formula here for P of x equals a specific k was the thing with all those happy exclamation marks. N factorial over k factorial, n minus k factorial, p to the k, 1 minus p to the n minus k. Just a really excited problem. So you know n is 5, k is 3, and you know that p is 0.7. So let's fill all that stuff in and then dissect this a bit. So we have 5 factorial over 3 factorial. 5 minus 3 would give us 2 factorial. P to the k, 0.7 to the third. 1 minus p would be 0.3, and that's to the second. And let's first just kind of review what this is. So the chances that 3 people recover, well, if you had somebody recover, 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 not, each of these has probability 0.7. That's where the 0.7 to the third comes in. The not, well, that's 30% chance someone doesn't recover. So 0.3 squared. That's where that number is coming from. What this number is doing is it's counting all the ways that you can arrange those recoveries and nots. You could have had first person recovers, second person recovers, next two don't, last one does. Could have had recover, not, recover, recover. And to count all the different ways to arrange those R's and N's that are special. And this number does that. So let's simplify that. That's 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. If you have a calculator that simplifies factorials, I don't care if you use it, but this isn't so bad. Look at that 3, 2, 1. Cancels with this 3, 2, 1. And that 4 and that 2 cancel a little bit as well. So you end up with 10 times 0.7 to the third times 0.3 squared, which comes out to be 0.3087. So about a 31% chance that exactly 3 people get better. And just remember that this 10 is counting the number of ways that you can arrange these. And just for kicks, you could see if you can find all 10. Okay, what are the chances that 2 or more people in the sample recover? This is probability that x is bigger than or equal to 2. And there's a hard way and there's a slightly easier way. So 2 or more people means 2, 3, 4, or 5. You'd have to do the thing that we just did for every single one of those. Or you could observe this is the same thing as 1 minus the probability that x is less than 2. So it's the complement of nobody or one person recovering, i.e. 1 minus the chances that x is 0 plus that x is 1. And you still have to find those two things, but not four things. So probability that x equals 0, no one recovers. Well, that's 5 factorial over 0 factorial, 5 factorial, 0.7 to the nothing, and then 0.3 to the fifth. And I know it's odd, I'm so sorry. 0 factorial is defined to be 1. This just is. Accept it, move on. Okay, done. So this works out to be just 0.3 to the fifth, which you really could have gotten without using that formula, right? I mean, if no one recovers and there are 5 independent trials, that's 0.3 to the fifth because that's 0.3 multiplied by itself 5 times for each patient. Okay, for 1, well, that's 5 factorial over 1 factorial times 4 factorial, 0.7 to the first, and then 0.3 to the fourth. That comes out, oh, sorry, this first one came out to be 0.00243, and this one is 0.02835. So back to the question at hand, this is 1 minus the sum of those two numbers. Which comes out to be 0.96922. So pretty good chances that 2 or more people are just are gonna get better. Okay, now this is a continuous distribution. So find the probabilities for x equals pulse rates of marathon runners, for which the mean is 60 and the standard deviation is 5. We're going to assume we have a normal distribution, which means we're going to use our z-table. Okay, so what's the chances that we find a runner whose resting pulse rate is below 49? The first thing you have to do is find that z-score. And that formula is x minus mu over sigma. The x in this case is 49. Our mu is 60 divided by 5 works out to be negative 2.2. So the probability that x is less than 4.9 is the same as z is less than or equal to negative 2.2. If you think about that bell curve, remember your empirical rule tells you that 95% are between plus or minus 2 standard deviations. So this person is in that bottom 2.5%. So the number that we should get out should be less than 2.5% or 0.025. And this comes out to be 0.0139. Which is less than 2.5%, as it should be, because this, we're saying what's the chances they're there or lower. Okay, next, how about you find a marathoner whose pulse rate is above 62? Well, first we'll find that z-score. Notice that this is not very far from the mean. So 62 minus 60 over 5 comes out to be 0.4. Now, one problem you have is these z-tables by default do less thans. And what you're looking for is, in your bell curve, if you're at 0.4, what's the area from there to there? And you can find this one of two ways. You can either do 1 minus the probability that z is less than or equal to 0.4. So that will be 1 minus 0.6554, or 0.3446. Or the chances that you're bigger than 0.4, just using some symmetry. Look, negative 0.4. This is the same thing as the probability that z is less than or equal to negative 0.4. And your table does that direction, and you get 0.3446 directly. So whichever way you like, I don't care which one. What this one does is it does the total curve minus this thing in purple that I just shaded, and then gives you the area of the black region. All right, what's the chances I'm going to find somebody with a pulse rate between 49 and 62? Well, I'll always be nice here, and I'll give you things for which you've done the z-scores already, so you have to do it again. So probability that negative 2.2 less than or equal to z less than or equal to 0.4. And I think pictures are pretty helpful here. You want the area in between a z-score of negative 2.2, which is way below the mean, and 0.4, which is pretty close to the middle. That's what you're looking for. Well, what you could do is find the chances that your z is less than or equal to 0.4. That will shade all of this stuff. You need to take away this little tail down there. So you subtract probability that z is less than or equal to negative 2.2. Now this we found was 0.6554 in our computations for part B. And then we take away 0.0139, which comes out to be 0.6415. So quite good chances of finding a marathon runner whose heart rates are within that range. The final chapter you're going to have on this exam deals with sampling distributions. So if you take many samples of a fixed size, how much can you expect the mean to vary among those samples? We do this for all sorts of situations. We have proportions and difference of proportions and means and difference of means. 5 different things in total. So start with proportions. In a random sample of 500 adults, 300 individuals say that they believe in love at first sight. So find the value of p hat, which is the sample proportion that believes in love at first sight. So p hat is 300 out of 500, which is 3/5, or as a decimal if you want to, 0.6. Okay, next find the standard error of p hat. Well, that's the formula root p hat 1 minus p hat over n. So 0.6 times 0.4 over 500 comes out to be 0.022. So next, why in part A did you find the standard error of p hat and not the standard deviation? What would you need to know in order to find the standard deviation? So to find standard deviation of p hat, one needs the true value of the population parameter p. As you only have an estimate, that p hat thing, you are finding standard error. Which is an estimate of standard deviation. all those problems that you did that found standard deviation, they said, oh, suppose we know the true value of the parameter is actually blah. And in that case, you could find standard deviation. So researchers would like to know whether the proportions of elementary school students who are obese differ in rural and urban areas. You know, things like maybe those kids in cities don't get enough exercise. So the plan is to take samples of 1,000 children from urban areas and 500 from rural areas. That maybe is just due to sampling difficulties. So we're going to have population 1 to be elementary school children in urban areas, and population 2 to be elementary school children in rural areas. So define in words what's meant by the parameters P1 and what's meant by P1 hat. So P1 is the proportion of, well, population 1 was urban, of urban students who are obese. And I should say it's the true or the actual, the unknowable one. P1 hat, this is the proportion of urban students who are obese in your sample. Okay. Suppose that unknown to the researchers, the true value of P1 is 0.2. So 20% of the students in urban areas are obese, and in rural areas it's 15%. Find the mean, standard deviation, and all this fun stuff, shape of this sampling distribution. So the mean is P1 minus P2. So 0.2 minus 0.15, 0.05. So on average, there'll be a 5% difference, and there'll be 5% more obese children in urban areas. Next, find the standard deviation of P1 hat minus P2 hat. The formula there is a big old square root sign. P1, 1 minus P1 over N1. P2, 1 minus P2 over N2. And this will tell us how much our samples will vary if we do lots of samples of size 1,000 in the urban areas and 500 in the rural areas. So 0.2, 0.8 over 1,000 plus 0.15, 0.85 over 500. That comes out to be about 0.020. And then the shape, this is going to be approximately normal. And here's what it would look like. The mean is at 0.05, one standard deviation away, 0.07, one below, 0.03. One more up, 0.09, one more down, 0.01. And most of your data that if you were going to do this, you'd find those differences are in between these things. Now, one important thing to be able to distinguish is the difference between mu sub d, which is the mean of paired differences, and this is the difference in two populations. And the hint there, two populations, two separate means. Paired really means a set of data where you've got a bunch of pairs. So one thing. So ask yourself, is there a natural pairing that's happening, or does it make sense to treat these things as two distinct groups? So we have 20 sophomores are randomly selected from campus dormitories at a college, and 20 other sophomores are randomly selected from students who live off campus. So we have people in dorms, people off campus, and we're going to compare the mean GPAs of the groups. So is there any natural pairing, like you put like a sister in the dorm and a sister in the off-campus housing? No. So these are two different groups. In which case we're looking at mu1 minus mu2, as in GPA group 1, and actually average GPA, minus average GPA group 2. So 13 individuals take a strength test before and after they participate in a 6-week training program. Now the big hint there is before and after. The investigator wants to compare the average gain in strength due to the program. Well, because we have two measurements on one person, there's an obvious pairing. You can pair their before and their after. So this is paired data. One individual has two measurements. And the symbol for that is mu sub d. So, vehicle speeds at a certain highway location are believed to have an approximately normal distribution with mean mu equals 65 and a standard deviation of 10. So, the speeds for a randomly selected sample of 25 vehicles is going to be recorded. So give numerical values for the mean and standard deviation of the sampling distribution of possible sample means for randomly selected samples of 25 from this population of vehicle speeds. So the mean, if you were to do lots of samples, is still equal to 65. But now the question is that how much is that mean going to vary if you take samples of 25? So that's the standard deviation of x bar, which is, remember, sigma over root n. And sigma here was 10, root n is 25. So 10 over 25 ends up being 10 over 5, which is 2. Use the empirical rule to fill in the following blanks. For a random sample of 25 vehicles, there's about a 99.7% chance that the mean vehicle speed will fall between what and what? Well, mu plus or minus 3 standard deviations of x bar. So 65 plus or minus 3 times 2. So 59 and 71. So if you took lots of samples of size n equals 25 and then found the average of them, this is where the average falls. Really almost all of the time. It's not talking about individual speeds, it's talking about the average of a sample of a specific size. So suppose you go to this place and you sample 25 vehicles and your sample mean is 55. You found x bar is 55. Is this unusual? Is this consistent with the fact that you think the actual mean speed is 65? So x bar equals 65 is not consistent with mu equals 65 And the reason is that this sample mean isn't included in what you expect it to be almost all the time. So the sample mean is outside the interval in part B. So what this probably leads us to conclude is that at this location, average speed may actually be below 65 equals mu. Like that assumption that mu is 65 is probably wrong, or you just had a bad day with bad traffic. One of those two. The mean and standard deviation for the heights of adult men are about 70 inches and 3 inches respectively, and for adult women it's about 65 inches and 2.5 inches respectively. Heights within each sex are bell-shaped. Suppose random samples of 9 men and 9 women's heights are measured, and the difference in sample means is found. So what is the mean and standard deviation of the sampling distribution? So the mean will be mu1 minus mu2. And I asked you to use men minus women just to keep it positive. So the average height for men is 70 inches, for women it's 65. So the average difference you're going to see between those two populations is men being 5 inches taller. Standard deviation, if you take samples of 9 from each gender, how much are you going to expect this to vary? Well, the formula for that was sigma 1 squared over n1 plus sigma 2 squared over n2. And both of those n's are 9. Okay, sigma 1 was 3. So 3 squared over 9. 2.5 squared over 9, which is about 1.3. All right, sketch a picture of this sampling distribution similar to the one in your textbook on page 346, or similar to the ones we drew in the earlier lessons. So the mean is at 5. It's going to be approximately normal. Plus or minus 1 standard deviation, we've got 68% of our peoples or samples. So 6.3, 3.7. 2 standard deviations away, well, that's going to get us to 7.6 and 2.4. And one more gets us almost everybody, 8.9 and 1.1. And so roughly speaking, looks like this-ish. Now, note that if you got a negative number, so what would that mean? Well, that would mean that in your sample, women were taller than men on average. Which certainly is possible that that would happen, but this thing tells us is like quite unlikely because 0 doesn't fall within plus or minus 3 standard deviations of this mean. Okay, and lastly, one important concept to hit on before we're done with this unit is as your sample size increases, what happens to these sampling distributions? And so you've seen things where you've had different sample sizes and drawn the pictures, and what happens is that bell curve narrows and gets taller around the mean. You're going to see less variability with big samples. So less variability with big samples. And what happens is this bell curve narrows and gets taller around the mean. Well, that's it for reviewing for midterm number 2. I hope it helped, and good luck studying.